Hey everybody, just wanted to do a quick quiz review with you guys. Apologize for the noise in the background. My children are watching Scooby-Doo. Okay, so this first question, the induced fit model. Now our options are substrate changes the shape upon substrate binding. Substrate must be the exact complementary shape. Now that one describes more of a lock and key model. Substrate changes shape to fit the enzyme. Substrates don't tend to change shapes. It's the enzymes that are actually going to change their shapes. And then the enzyme changes their shape upon converting substrate to product. That might be true, but that's not what induced fit means. That would happen after, let's say, that happened. So the enzyme is going to change its shape upon substrate binding, and then of course when the substrate's gone, it'll change back to that shape that it was previous. So that's why that last answer would be true, but that's not what induced fit is. Question 2. Which of the following is the best definition of an active site? The least stable reaction intermediate. Well, the active site is not a participant in the reaction. The amino acid residues in the active site might be, and the substrate definitely, but not the active site as a place. A gym where enzymes work out? No. Reactant in an enzyme catalyzed reaction? Again, like the first answer, it's not an intermediate, it's not a reactant, it's not a product, it's a place. So it's the site on the enzyme where catalysis takes place. Man, there's a lot of typos. How do enzymes increase the rate of reaction? You guys got this one 100% right. Nobody missed that. Lowers the activation energy. Number 4. What is the Km of an enzyme? Well, it's all of these. It is a simplification of the rate constants, and we can talk about the rate constants with question 5. It's a measure of the affinity for the enzyme, or it can be used as a measure of enzyme affinity for substrate. But what it specifically is it's an equivalent to the concentration of substrate needed to reach 1/2 of Vmax. So the answer is all of the above, or all true. Now, as I mentioned with the K1, the K-1, and the K2, these are the directions of enzyme catalyzed, well, this is what I'm trying to say, enzyme and substrate forming, enzyme substrate complex. That can be defined with a K constant, an equilibrium expression. Now the reverse reaction, ES going back into enzyme and substrate, can be described as just the reverse of that original equilibrium constant. Now these two are in equilibrium with each other. These two are the majority of what the reaction is doing. The step that happens sometimes and less often is K2, where our enzyme substrate complex actually releases enzyme and then product. So then going back to the question, this question is saying which one of these is the rate limiting step? Well, it's not going to be F plus U plus N is fun. It's not going to be ES, the enzyme substrate complex, breaking down into the enzyme and substrate. That happens actually quite often, just as often as the enzyme and substrate form to make ES. But remember, ES now has an energy hump, that activation energy that has to be overcome, and that's why sometimes these things just dissociate. But sometimes ES will form EP, and that's the answer. What is the Vmax of an enzyme? Well, the Vmax is the maximum velocity or rate that an enzyme can achieve. And so that's why it's not the slowest rate. It's not the same as K2. K2 is an equilibrium constant. Vmax is a speed. Let's see, it's not a constant. It's different for different enzymes. Vmax is something that an enzyme can reach, but it is not always there. So it is the maximum rate. And question 7 ties into that. Which one of these points could be used to plot or to determine the value of Vmax? Well, Vmax is the top of the curve, so where the curve starts to flatten out. And so you can see here points A, B, and C. Point C is the only one that's showing us kind of a line where that curve is approaching, the maximum speed. So it's C. B and A are useful for determining Km. You would need to know what the half speed is, so you'd need B, and then you'd want to see what the concentration is at that half speed, and that would be what Km is. It's the concentration or whatever the point A is pointing to. Have I been answering these? This is C. Question 8. What is the value of Vmax as determined from the Lineweaver-Burke plot? So in this equation, or in this problem, we're given an equation. You can kind of see it there. And so we've got a slope, mx, m is the slope, and we've got a y-intercept. The y-intercept here is 0.0197. And so I'll just jump over to my whiteboard real quick to show you. If we're looking for Vmax, all we need is to get the y-intercept and set it equal to 1 over Vmax. If we were looking for Km, we would need the x-intercept, and we'd set that equal to negative 1 over Km. Now, how do you get the x-intercept from an equation like this? Well, you set y equal to 0. Y equal to 0. That way on the y-axis, there wouldn't be any rise. It would only be an x point. So you set y to 0, solve for x. That's your x-intercept. Of course, when you're looking for Km. The answer here, if you do that, comes out to be 50.8. Question 9. This enzyme is sometimes used as a chemotherapy agent, the enzyme asparaginase. The graph below plots rate versus substrate for 2 different asparaginases, and the question is which has a higher affinity for asparaginase? Well, if you remember the hemoglobin and myoglobin binding curves, you'll remember that for hemoglobin, we said, I'll just jump to it. For myoglobin, our curve looks something like this, and we said that made myoglobin good at storing because it has a really high affinity. And then hemoglobin's was like something like this. It was much, there was more of a sigmoidal shape to it. So what you can do is you can look at the speed, the initial rate. If the initial rate is really high, then that means that a lot of enzyme is binding to substrate. And so that's going to indicate a high affinity. And so here, asparaginase 2 looks like it has the higher affinity because it reaches a higher speed earlier in the concentration of asparagine. It takes a lot longer for asparaginase 1 to get to that same speed, and so the affinity then is what's lower. They're not finding each other as quickly in the solution. So 2 is the answer there. What type of enzyme catalyzes this reaction? Well, if you look at what's happening, the hydroxyl group on the top of lactic acid has been oxidized into a carbonyl group, and NAD plus has been reduced to NADH. So this is definitely some kind of oxidation reduction. So we're going to call that an oxidoreductase. Which of the following is a type of catalysis that occurs in enzymes? Covalent catalysis, near attack conformation, and general base catalysis. These are all examples. We didn't go over near attack, but we did talk about covalent and general base catalysis. And so just those 2 being correct means that they have to all be correct. In the catalytic triad of chymotrypsin, what's the role of serine? So if you remember, serine has a hydrogen, an OH group, a hydroxyl, that it's going to donate a hydrogen to histidine, or histidine actually is going to remove it. And then serine is going to play a role in forming a bond to the carbonyl group of our incoming peptide, and to form the acyl intermediate, the enzyme acyl intermediate. And so it's a nucleophilic attack, if you remember, of the oxygen in that serine. And so this is going to be a covalent catalysis. Covalent because we're going to form a covalent bond here. Nucleophilic attack would be a covalent catalysis. What is the role of aspartic acid in this first step of chymotrypsin? Now the answer here is it stabilizes the correct histidine tautomer. If you look down at histidine in the picture on question 14, you see that histidine has 2 nitrogens in that ring. Well, the fact that one of those hydrogens is participating in a hydrogen bond with aspartate, or the aspartic acid, well, it is aspartate in that form, means that histidine is not only locked in place like that, but we're not going to have flipping of that double bond. That double bond there could jump back and forth on this histidine, and that means either one of those nitrogens at any given time could have a hydrogen on it. But we don't want either one to have a hydrogen. We want only the one facing aspartate to have the hydrogen, so that the other nitrogen is free to do general base catalysis. Okay, so that is the role of aspartate there, is to make sure histidine's facing the right direction and that the nitrogen has lone pairs on it. Question 14, what type, I'm sorry, be nice to your brother, please. What type of catalysis is occurring in the following step of chymotrypsin catalytic cycle? We see two things here. We see the nitrogen on histidine pulling a hydrogen off of serine. So that is obviously not sorcery. That is general base catalysis. That's nitrogen acting as a base. The reason it's not specific base catalysis is because we're not using hydroxide, OH minus. That's specific base. That's my boy screaming next to me on the floor. General base catalysis. The other thing we see happening is that the serine's oxygen is going to form a bond to carbon of the peptide. That is that covalent catalysis that we talked about already. So that is going to give us, this is an answer, general base and covalent catalysis. 15, which statement best describes what is occurring in the following step of the chymotrypsin catalytic cycle? We see here nitrogen pulling a hydrogen off of the water molecule, and the water molecule doing a nucleophilic attack on the carbonyl. So are we forming a acyl enzyme intermediate? No, that's already formed here. That's what the serine attached to the rest of that stuff is. Are we forming a low barrier hydrogen bond? No, I don't see any hydrogen bonds forming. Are we deprotonating water and nucleophilically attacking the enzyme acyl intermediate? Yes. Is there a nucleophilic attack of the substrate carbonyl? Yes. But is it by serine 195? No. It's by the water molecule in this question. Last question. Which of the following corresponds to the slow step in the chymotrypsin catalytic cycle? Nobody got this one wrong. The hydrolysis of the stable acyl enzyme intermediate. Those of you that remembered the example of the p-nitrophenol, remember that there was a burst phase in which the p-nitrophenol was released, and then a secondary state where the acyl intermediate undergoes hydrolysis. That's what's happening here. All right, guys. Hopefully that helps if you answered any of these wrong, and I'll see you guys next time.